chemical shift. So this chapter is going to be where the location of the peaks, where we expect to see the peaks. And as I mentioned earlier, the location of the peaks is going to differ depending on the operating frequency of the instrument that you're using. And so what they do is to normalize everything, they define the location relative to the frequency of a reference compound, and in this case is trimethylsilane. So in this one, at 0, we have trimethylsilane. Here we have upfield protons. These two protons, or two types of protons, are shielded, and down here we have deshielded protons. Now the deshielded protons are close to something that's going to withdraw electron density. So here we've got a methyl group. Its protons are going to appear at about 1. So they're going to be right in here somewhere. If we add an iodine, then we shift it down to 2.2. Bromine is a little more electronegative than iodine, and that moves it to a 2.7. Chlorine is even more electronegative, and finally fluorine is the most electronegative, and that moves the hydrogens that are attached to the same atom all the way down to a 4.3, or right in here somewhere. Let's go up here. If we look at this here, we've got a chlorine. I'm going to draw the chlorine in this color, and we'll go back to the blue for the rest of it. We've got 2 hydrogens here. They're on the alpha carbon, and they're going to appear at 3.3 ppm. The 2 hydrogens that are here on our beta carbon are going to appear, these are hydrogens, and they're going to appear at 1.6 ppm. So these first 2 have been downshifted quite a bit. The 3 hydrogens on the gamma carbon are not affected, and they appear at 0.9. So the effect is most significant for the alpha protons. The betas are affected slightly, and the gamma not at all. So I've got some numbers here. If we have a methyl group and it's not affected by anything nearby, then we can expect its peak to be at 0.9. That's this right here. If we have a methylene group, that's a carbon with 2 hydrogens attached, and it's not close to anything, we expect to see it at 1.2. A methine is a carbon with a lone proton. We expect to see it at 1.7. So we can come up with this, we're going to come up with a table that is going to give us an estimate of what the downshift should be for different groups. Okay, so if we have an oxygen and it's involved in an alcohol or an ether, we expect the alpha proton to be downshifted 2.5. The beta proton is going to be downshifted 0.5. So let's look at an example. And let's change some color here. This is a methylene group, the red here. It's a CH2. We expect a methylene group to be at 1.2. Because this carbon is right next to an oxygen, this is the alpha carbon, we have to add 2.5 to it. That number comes from right here. And we'll expect to see the two hydrogens in pink at 3.7. If the oxygen is an ester, I'm going to go back to blue, we expect to see a shift of 3. And on the beta, it's 20% of that, so it's 0.6. So let's look at this example. We've got an ester. Remember what an ester looks like. That's an ester. And we have our two hydrogens of interest. These are the two we're looking at. These are methylene, and so we'd expect them to be at 1.2. However, because they're right next to, this carbon is right next to this ester, we'll have to add 3 to it. And we'll expect to see this one at 4.2. The actual chemical shift is 4.1. So this is an estimate, but it's a pretty good one. So what if we have a carbonyl group? Carbonyl groups, oops, I'm going to go back to blue. I like blue. 1 and 0.2. So let's draw our molecule. And this is a carbonyl group, like a ketone. What I've drawn there is a ketone. And we're going to be interested in these two hydrogens right here. These are methylene groups, so we would expect them normally to see them at 1.2, but they are alpha. This carbon is alpha to the ketone group, there, the carbonyl group, so we'll have to add 1, and we'll expect to get to see it at 2.2. And the actual here it says is 2.4. So, like I said, it's an estimate. So let's predict